In this video, I'm going to show you how to use the PV battery configuration tool as a itemized protected load design with DC coupling. So first of all, let me just show you a little bit about this tab. This is the Insulation Loads tab, and as it suggests, we are going to input our loads, our AC loads or DC loads, and our insulation. We'll get that from PV Watts or another resource. These little brown cell marks right here and here all the way through this configuration tool indicate that you need to input something if you're going to get anything back out of it. All of the green cells are cells that you can actually change. You can put something into them. There's a drop down. Let me just come down just a little bit below here. It says calculate from itemized AC loads or calculate from main AC loads. Depending on which one you select, the tool will design the system based on the loads that you input, either from itemized, which is all of these in this chart, or the ones that you put in just in this line right here. Now we're going to do the itemized loads. That's what we're going to design in this, but we're going to also show you how you can do it with the main AC loads as well. If we're doing itemized loads, that means we're building a PV array and a battery bank and an inverter to serve these all the time. Treat it as if it's off-grid all the time. Even if it's a backup system or a bi-modal system, or even if we want to use it for self-consumption modes, we're going to design this as if it's going to operate off-grid all the time. So you want to list down all of your AC loads that you're going to put into this protected loads panel. So if I have identical loads, I can set the number here and say how many of these I have. So if I have 4 at 15 watts, then I have a total of 60 watts running. Most of these loads are single loads, such as the refrigerator, the microwave, toaster, all these type of items. And I've listed out the continuous rating of this device. The refrigerator looks kind of funny, only 60 watts. When your refrigerator runs, it uses a lot more energy than that, but they give us guides on energy usage based on a 24-hour period, or better yet, an annual period. So I've broken it down into 24 hours of usage, and you can see where I've kind of moved this around a little bit. The device is designed for an atmosphere somewhere around 70 to 78 degrees. If we're running a little cooler than that during the winter, then we actually have a higher efficiency performance. So I've shown fewer hours during the winter months. Anyway, you can do that or just make it all 24 if you want to. So I've tried to identify each of my months and the number of hours that the load occurs each day during that month, so that my true usage map is more in line with what I actually do, my actual behavior. Now these brown input cells, you don't really need to put them in. You can do the surge load for motors, startup loads if you want to, but most of the time with your average loads on a residential backup panel, your critical startup loads are not going to be that demanding, and so your inverter will usually be more than capable of delivering the startup load. The only time you really need to do this is if you're setting up a shop and all of your loads are startup loads. In that case, you really have a pretty serious startup demand and you need to pay attention to it. But for average loads in a home, not the case. Same thing with power factor, this other column here in brown. You can identify the power factor for the particular load. Like this refrigerator, may have a 0.6 or 0.7, and that does affect the demand on the inverter. I'll leave it all set at 0.9 because a lot of these are on the same circuit, or they'll cancel each other out when it gets to the inverter. So we usually end up with somewhere around a 0.85 or a 0.5 power factor. So mine's set at 0.9. So we identify all of these loads that we're going to put into this protected loads center. We identify our usage, and then it all tallies up down below. These blue cells are the totals. So this is the average daily load per day in January, February, March, April, and so on, all the way through the year. Over to the left here we have the total connected load. We have that identified as 5358. That's if everything was turned on at the same time. That's highly unlikely, so our blue cell is calculated based on the largest single load plus 50% of the other loads. This usually covers you pretty well on load demand into the inverter. So this information is going to be fed to another tab, another page that we're going to look at. Then on the far right we have the average. All of these daily loads are averaged up, and our battery bank is sized based on the average daily load. So all these blue cells are going to be our design cells. Now you notice that I have my kilowatt hours of my main AC, so what I'm using from the grid on my main AC before I pull all these loads off, this is the load demand. So we're not going to design the PV array or the PV system to serve this. We're just going to take a look and see how we're offsetting it. So let's drop down. We've done all that work, and now we want to put in some information. We need to put in our solar radiance data, our sun hours, depending on the location of our PV array and the tilt. So the azimuth and tilt have an effect on the actual sun hours you receive at any one location. And then there's another factor. You usually have some shading from trees. If there's no shading, then you can just go to PV watts, put in your azimuth and tilt, and it'll give you an accurate sun hour reading for each month of the year. If you do have shading issues and you want to use the Pathfinder, the Solmetric Sun Eye, and get a good reading on that. So both of these are the results of using a Solar Pathfinder. Now I've selected column 1. If I select column 2, it changes things. The tilt is greater. So we're getting better performance during the winter months and worse performance during the summer months as far as the solar radiation that we're collecting. And you'll notice this little blue cell over here on the left side. Notice how that changes when I select from one to the other. What it's doing is this is sending this information up to this row, and there's a calculation going on. That's the loads to sun hour ratio. It's taking these loads up here, dividing it by the sun hours, and dividing by the conversion efficiency down here. We've got it set at 70%, and giving you a one-to-one PV array output necessary to offset 100% of this demand. So our largest demand, our ratio, is 2.7. It occurs in December. I've got this set to factor in 120% extra PV array size for recovery. So my 3.3 is increased by 120% above my 2.7. If I change this to column 2, then this worst month of the year is still in December, but it dropped down to 2.6. So that I now need a 3.1 kW PV array. So sometimes you can adjust your demand load by changing the direction or the tilt of the PV array. So we've done that. This is really all we have to do on this page to do a DC coupled system with itemized loads. And we have, I'm going to go back to the one, so 3.3 or 3.1 kW PV array. This information is being fed into these other tabs. We're going to go into the DC coupled tab, the next one. And we're going to select the battery voltage. So we're going to go ahead and set that. That has to do with quite a few things in sizing. So we're going to go ahead and set that battery voltage. 48 volts is what we're using. Next thing we're going to look at is selecting a PV module. So we find out from our distributors what they're carrying, what we can get our hands on, and go into this database and select the module. There's thousands of them in here, so everything you are looking for should be here. So you pull that in, and all the data pulls in about this module. And we also have the size of the PV array being fed over. And so it automatically says, oh, well, with this module, you'll need 11 modules to accomplish that 3.3. Say, okay, we'll see how that works out. We also want to set our temperature parameters for the location, the ASHRAE maximum and minimum temperature. And I have a little drop down here that allows you to increase the cell temperature. We know about 25 degrees increased cell temperature is pretty normal. You can increase that further if you think that, that it's going to be in a hotter environment, or cooler if you think it's going to have a lot of air blowing around it and good breeze. So you can just adjust that as you wish. That will affect the number of modules you put in a string in these various charge controllers. So let's go down to the charge controller. Now that we've selected our PV module. Oh, one thing before I go down there, you'll notice that we have green inputs for modules up here. If for some reason the module that you're looking for is not in the database, let's go to the top of the database, all the way at the top. The default mode is for it to be just set in select module here, and it'll have nothing across. The first one you come to is 0. And that basically that is saying if you put something in up here, and I'm going to go up and show you what that means. Let's go X, Y, Z, and you'll see now when we slide back up to that, that's what populates where the 0 was. So now you can put that in and select that first position, and it'll give you that data that you put in. So anyway, need to leave that option in there just in case we don't have one. Alright, on down, let's go down to the charge controller. Same thing with the charge controller. You can input this information if we don't have one in our database. Or you can just select from the database the product, and we have most of them that are available to you. We're using Outback and Xantrex, or Schneider rather, on these options here. So we have 4 selections. You don't have to use all these. This just gives you a lot to look at so you can pick the best charge controller for the arrangement. So we have an Outback 60, an Outback 80. They also have a 100. Let me just pull that one down. Let's go ahead and get the Outback 100. Okay, we have those options. What it's looking at is the 11 modules we're trying to achieve, and it's trying to achieve that here. And it says if you use the 60, you can put 10 modules per controller without oversizing capacity to that controller. You can check with the manufacturer. Possibly you can exceed 10, but you'll have to get permission to do that. And so it says you need 2 controllers to hit 11. That's kind of excessive. And then with the FX80, we just need 1. We can put 14 into that controller, and of course with the 100 we can put a 17 into it. Not necessary, we just need 11, so we're going to overkill just slightly with the FX80. So anyway, you get to take a look at all these different options before you make up your mind, and then when you do make up your mind, you go down here and you select 1, 2, 3, or 4 from these. And if we selected this one, it tells us how many we can put in series based on this 150 volt max. What's the minimum number you can put in series, because we want to stay above. I use float voltage because I want to get those batteries back up fully charged during the summer months, and float is not to the point of absorption, but it is adequate. So I use that as my minimum. You can go a little above that if you want. You can just take a look over here, and you can see that with 2 in series, 57, that's probably adequate. With 1 in series, definitely not. 3 in series, very good. So our automatic design tool picks 3. It says, hey, that looks really good. I'm going to go with the maximum on that. But it tells you need 2 controllers. So let's go to the next one. It says 3 is series again, 4 in parallel. So that's 12. That's not 14. Why can't we get 14? Well, because we have, I mean, we could. If we put 2 here, you know, then that, well, that gives you 8. Let's see, if you put 2 and 7, that give you 4.2. You could go up to that point. You can get that many. But we don't need them. We only needed 11 in the first place. So let's go back to that. And says we need 3 in series and 4 in parallel and 1 charge controller. So it's designed it for us. We don't have to do anything. If we want to accept that, then we don't change anything here at all. We just let that be the number. If you wanted to change something, you can. You can change this to 2 and do it however you want to do it. It's a little bit low. And if you needed more than 1 charge controller, you could do 2. Say, hey, let's beef it on up. Now we have a 7.2 kW PV array. Or you can go over here in these inputs and say, let's do 3 and 2 and 1. So we have 1 charge controller that's putting out 1.8. I'm going to go back and put 1 in here, and 3.6. So now we have a 5.4 kW PV array. So you can do that if you want. We don't need to for this example. We have met our requirement. 3.6 is more than what we need. Is that a problem? Not really. PV modules are not that expensive these days. So that's all you have to do on this page to match up your charge controller to your PV array and module. You do have the option of selecting another charge controller down below. So if you had a large PV array and you didn't want to use multiples of a particular charge controller, you could go down here and select a different charge controller to add into the same PV system. If you want to use the same module, just click Module Selections and it'll identify the same one you selected above. Or you can go pick another one. I wouldn't do that. I would use one module for everything. And so we're not going to design any more down here, so we're going to go away. So this is just a duplicate of the same one that's above, but it allows you to add complexity to the system if you want to. So now we've done all we need to do on this tab. So we're going to go to the Design Inverter Battery tab. So let's go to the top of this slide. Here we have green inputs again, as we did before. We have the inverter we can select from our database of inverters, or we can put one of our own. If we have some brand new inverter that came out that is not in the database, then you can put that in. You'll notice up here it pulls in the 3.3 kW PV array we are required to have. And then it also has the one that we actually designed. It says, you just designed one that's 3.6, so that's the dominant number on this slide. So, okay. If we had done AC coupling, at this point in time, we could go to our interactive inverter configuration tool and pull the information off of it, because we would not design the AC coupled PV array and inverter with this tool. We do it with a separate one. So let's say we had a 300 watt PV module. Well, there it is. It said 11 of these. So you'd put 11 in here. And then you'd find an inverter that you designed with. And now you would have the AC coupled system pulled into your battery-based system. So it's pretty simple. Just 4 little inputs that you have to pull in from your interactive configuration tool. So we'll show you how to use that one in a separate video. Alright, so enough of that. Let's drop down and go ahead and pick our products. The green shows us that we have a demand of 3.6. Our surge was 6.9. We need to find an inverter that's rated 3.6 and has a surge up to 6.9. Now I've selected the Radian 4048. It's a 240 volt model. Has a max continuous current of 16.5 amps. Shows that it'll supply all of our loads, but in surge we may have a problem. So in that case we may want to pick something else. We could double the size. It doesn't cost all that much more to double your capacity, and then you would never ever have a shutdown event or an overcurrent event or a voltage collapse. You get these kind of events whenever you have too much of a load feeding into your inverter. So anyway, so something to think about. Let's go back up. Use the same one, the original one. We're taking a chance, kind of living on the edge here. All right, so it automatically tells you how many inverters you need. You can override this right here, but if you don't want to, then accept what it told you. If this was a bimodal system, and and it's not, it's a standalone design. If it was a bimodal system, what it's going to do is look at your PV array and make sure that your inverter is rated to handle the PV array that you put into it. Well, it turns out that our load and our PV array are similar. A lot of cases, if you had added, let's throw in some AC couple up here, and let's see, put in 10, and you had one inverter rated at, let's say 3 kW. Sorry, number of inverters. Let me get this straight. 3,000 watts. Okay, you have to put it in right to make it work. Well, now we have a 6.6, and it's telling us we need 2 of these inverters. The reason it's telling us that is because this is a bimodal pass-through. So we're going to sell power back through this other inverter, and if you have a 4 kW inverter and you're selling 6.6, you're going to damage the inverter eventually. So anyway, that's just an example of how it will look out for you. And let's pull that out. We don't have that, and we are not going bimodal at this time. We're designing the standalone. Okay. So that's pretty simple to select the inverter, get the right size inverter for the system. Sizing the battery bank is a little more complex. It doesn't have to be, but it can be. So we have our average daily load, 6.3, that was fed over from our installation loads tab. And we have our 48-volt battery system. You know, once we select an inverter, if this is a 48-volt inverter, that overrides everything down here. So we can no longer change this with our drop down. It won't change anything. So once we pick our inverter, it's locked in. What we have, I'm going to pull this out. We have options to affect the size of the the battery bank based on how we want to treat this battery, you know, and how many days of autonomy do we want. Load fraction, 80% is pretty good. That's, you know, the percentage of energy that's actually being drawn from the battery. So during the middle of the day when your PV array is producing energy, you don't have to draw any of your load from the battery. So the load fraction is just the loads occurring after solar hours. So for this example, I had it set at 70%. And that being the case, I mean, if we had 100%, if all your loads were in the daytime, none at night, I'm sorry, put that the other way. There we go. Then you don't need a battery bank. Well, technically you do, otherwise the system won't run. But you know, you're actually not drawing any power from the battery bank, and it seems to be that you don't need anything. So you'd always want to leave a little something in there just to build the battery up. So if you had 100% load fraction, in other words, no loads during the day and just at night, then you have to have a larger battery bank. So I'm going to go back with my 70, and so you change this, and it will reduce the demand. If you had even loads throughout the day, and let's say 25%, so you would have 75%, then it's going to look like that. So anyway, it's a hard thing to nail down, but 70 to 80% is probably correct. So it says we need a 21.9, basically a 22 kW or kilowatt hour battery bank, and we'll have this is a lead acid battery that we're using, so we try to keep it healthy with 20% average depth of discharge. If you say, well, you know what, I think 25 is just fine, then you can do that, and it'll change this, and it'll reduce the size. So it allows a deeper discharge a little bit, and a smaller battery bank. So it's up to you. You can go outside of that 20%, but that's the max lifetime warranty that they give you with lead acid batteries. Okay, there's some fractions in there, obviously.
So now we have the battery bank, and we're going to go down here and select a battery. All you have to do now is just pick a battery, pick any battery, and it'll tell you, how many batteries in a series to accomplish your voltage, your 48 volt battery bank, and then how many in parallel to accomplish your capacity. And if you have more than 3 strings in parallel, it's going to give you a warning sign telling you that if you're using lead acid batteries, you got a problem. So it's going to restrict you from doing that. I'll show you. Let's use a 12 volt. Got that okay? Let me go with the lower capacity 12 volt. That may do the trick. Nope. Okay, there. It says we need 6 strings in parallel to accomplish this capacity, and of course it gave us the warning, excessive parallel string count. Let's go back and I think we'll be using this one right here, 1 string. So using a low voltage, higher capacity battery usually allows you to have fewer strings in parallel, so that's a general rule. So all this is showing you down here is the amp hours. It's giving you the amp hours as it relates to the kilowatt hours based on the battery bank voltage. And down below that it's showing the charge rate. If we have a lead acid battery, you can use the C4 as the very maximum charge rate. C5 is a little more cautious. And what we take a look at is, what is our charging source? We have 2 charging sources. One is the inverter. If the inverter is calling on a generator or the utility to charge, this is the charge factor based on that particular inverter we have. If we had 2 of them, it'd be twice this much, and we'd be at risk of overcharge. We have 1 charge controller rated at 80 amps, so it's listed right there, and all of those are looking at this. If these are higher than this, you'll get a warning sign over here. It'll say, hey, you're exceeding the capacity of charging this battery. It's possible that you could stress it. If you have a lithium-ion battery, we have this C2 charge rate, so you have a much higher capacity and less of a worry. So I leave this on C4 for lead acid, but bear in mind that's a little bit of a push if you're going to do that all the time. We also have a generator sizing down below, so this is calculating the size of the generator you need based on 175% greater than the inverter capacity. Yeah, take that out. Gives us the D rate. So if you have a higher temperature than it's rated for, and if you have an elevation other than sea level, then it's going to derate your generator for you. And you may have to actually override this and say, hey, maybe we need an 8 to get that. Okay, so that's basically it. You've designed the entire system, and you pretty much just selected random pieces of equipment, and it tells you, it gives you warning signs if you exceed a capacity. It tells you how many in parallel you have to have, and what your actual battery bank is compared to your requirement. So everything's designed. Way over here on the far right, there's a materials list. It tells you how many of what you need, and if you want to use this for sizing your conductors, you can. It's kind of a little cumbersome to go through all this, but at least this will list all the products that you have. Now let's go back. So we were on Design Inverter Battery. We're going to go to the right, hit Line Diagram. This is a DC coupled system, so we're not going to see any numbers for the AC coupled. We're just going to see DC coupled inputs. We have 1 charge controller, 1 PV module and array. So we list all the modules and the kW ratings of everything there. We see the line diagram description, and it's numerically indicated as to what everything is.
Drop down, we see the battery identified and the quantity and capacity, also the inverter, same with that quantity and capacity of inverters. And if you have a generator, then it shows up here as well. If you want to size your wires and conduit and overcurrent devices, this is the place to do it. It says you have charge controller, category A, up here at the very top. You have one circuit to account for. If you had other options that you selected from the DC coupled, the design PV DC coupled tab, then they would show up here. Or if you had two identical charge controllers with a PV array, then it would show up with two here. It would also show up with two down here, telling you that you need to build two circuits. It only says one. It says A, so you select A, and there it is. We have number of strings per controller is 4. Are they combined or are they parallel? Well, we don't, if it's a pole mounted system, we usually put them in parallel, we usually combine them, excuse me. So we'll have a combiner out there and just bring two larger conductors on in to the charge controller and all the equipment. If it's a rooftop, because of code requirements these days, we usually just pull everything parallel down. So you would have a total of 4 circuits, 8 conductors plus a ground, feeding in a conduit from the roof down to the charge controller, where you would have your main combiner and disconnect at that point. I had this set for combined because this was a pull top on a ground mount. So we had a 48.3 max current requirement, and then we multiplied it by 125% and we get our 60.3. And you could probably get by with a number 6. I'm using a number 4 primarily to combat voltage drop, and depending on which column you look in. So here we have an indication where we need to look. It says conductor size. Well, go to table 31015B16. So you open up your NEC, go to that table, select your conductor. And then while you're in there, go ahead and look at the ampacity for the column that you're in. Excuse that. And then you do the temperature D rates. So we have 2 tables, 31015B2A and 31015B3C, depending on whether we have a temperature greater than 30 degrees C where the conductors are running, and possibility that these are run underground and there's not that much exposed above the ground with this ground mount, so we may not have a D rate. If there's 10 feet or more in this higher temperature, then yes we do. If there's less than 10 feet, then we don't. And if we had, more than 3 conductors in a conduit, we have to do that D rate too. So in our case, excuse me, we had them all combined, so we only had 2 conductors and a ground. So it gives us our D-rated ampacity, and that is greater than our continuous current, so we're in good shape. We'll go to table 8 of chapter 9, and find our ohms per 1,000 feet for this number 4 conductor. Put that in. List the one-way distance from the combiner to the charge controller, and it'll calculate the voltage drop for us. Our overcurrent device, we see the increments here that pops up for you when you hover, and all we're looking at is something that will meet this requirement. Technically, we could drop those fraction lamps and go with the 60. Here again, you want to look at the NEC column in which the conductor is rated when you do this. Equipment grounded conductor, table 250-122. This tells us the size of the equipment grounded we use. Now all of these are embedded down at the bottom of the page here, of the tab. So 31015B16 is right here. We open it up. Let me, there we go. Blow that up just a little bit. So we can see our conductor. This is our copper 90-degree column. If our equipment and our conductors are all 90-degree rated, then we can use this ampacity. And then for our derated temperature, do the same thing. And with PV source circuits, we have to start at this point right here down. We can't use these, we can't increase the ampacity for cooler temperatures. So anything beyond the PV source circuits or output circuits, then we can use this table in its complete increased ampacity as well. So typically we have a derated factor down here. That'll reduce the ampacity of the conductor. Then of course we have the more than 3 conductors in a conduit. And if we have more than 3, then we have to derate by this factor here. And then we go to Chapter 9, Table 8. And let me pull that closer in to the, let's see, that up a little bit. And we see we had a number 8, and it was stranded cable 0.778, number 4, 0.308. So whatever conductor we're using, we want to make sure that we have the ohms per 1,000 feet, and it is in this highlighted red outlined column. So that's really it. We're doing the same thing over again with the output from the charge controller, and we also have the conduit. We can click on the conduit size. Also the grounding conductor. They ask for the let's see, get that where we can see it a little bit better. There we go. Maybe not that much. They're asking for the overcurrent device. So if you have an overcurrent device in place, then you want to use this as your guideline for the grounding conductor. If it's a PV source circuit and for some reason you don't have to have an overcurrent device because there's not enough parallel strings that exceed the capacity of the circuits, then you have to calculate the hypothetical and then use that as your guideline. So if we had 4 parallel strings, it's 8 conductors feeding through a conduit, then we have a what would that probably be somewhere around 70 amps, I think that was, right? And so we'd have to go up to number 8. So we don't have a 70 amp, we have a 60 and a 100, so you automatically have to round up to the 100 and go to the number 8 copper conductor. And then you do the same thing. You have your AC input and output. This goes to the protected loads panel, and the input comes from the utility or from the generator. And so you really want to defer to the manufacturer specifications on this. They usually do specify all of these, and you want to put in your conductor length so that you can get your voltage drop. Notice we have 2 voltage drops. One is from the output and one from the input, and then they're combined. This happens whenever you are in bimodal mode and it's in the evening hours, your batteries are full, and all the loads in the critical loads panel are being served by the grid. So it's going the full length of the connection from the grid connection into the inverter, and then from the inverter to the critical loads panel. So if these are on a long ways away from each other, and I've seen this happen several times, then you have a pretty significant voltage drop. We don't here, we only have 0.3%, that's negligible. But I've seen it where it got high enough that it would actually cause a voltage collapse, voltage drop, whenever some loads would start up. And this is always after hours, non-solar hours, whenever the grid was supplying everything. So look out for that. We also have labels that are generated down below. So if you keep on going, you see these numbers that correlate to the line diagram, and it tells you where these labels may have to go. And if you had multiple PV arrays, it would give you all those PV arrays out here, and the voltage, max current, and the controller current as well. So you can put those on each one of the labels. It goes to the DC disconnect feeding to your charge controller, to the individual charge controller. Going down, it gives you the battery information for your battery label, and then you keep going down and you'll hit your AC labels, so it'll give you the max continuous current and voltage that goes on that AC label, and then it indicates these other labels that are probably required at some point, maybe some are not. You do have to weigh in on a little logic and see whether you need all these labels or not, but here's where they're suggested to go, and it correlates to the line diagram back up here. Just find the number and the location. Last tab, let's go over here to the performance, and we see that we have our loads information fed in here. We have our PV array information fed in. We have our battery bank information fed in, and then we have our conversion efficiency. So we have that at the top. Then we have a chart that's showing us our sun hours, showing our PV array production each day, showing the main loads and the percent that we're offsetting of our main loads, and then our AC protected load center, and then the percentage that we're offsetting of the protected load center. So we're in great shape. This is a very well designed off-grid system. The worst month of the year, we're producing 132% more energy than what we're using. So we could stay off-grid without a generator most of the time. Maybe in some winter months you may have a couple of days where you're getting in trouble. But if you'll notice the recovery time based on a battery bank that's 50% discharged, we can recover the worst month of the year. It takes us 9 days to recover. You wouldn't want to do that all the time. You would shorten the life of your battery bank if it's lead acid. If it's lithium ion, not a problem. But lead acid would be a problem. But this is just the occasional deep discharge in about 3 months of the year that we have that. The rest of the months we recover pretty fast. If you only have 20% average depth of discharge, then you see that it's a very short period of recovery, and that's pretty typical. So you can change that, and let's say it was 80%, then it gets a little bit more serious. I used to leave it at 50 because that's pretty typical of extreme cases that we see. Then we look at our chart. I must have a, hold on, what? Yep, 1370, not 1370. Bad input. Go back out. There it is. So this is the typical consumption curve for this this home. This is the off-grid protected load center load, our PV array. It's above the screen line. That's what it needs to be. Then our battery bank, of course, is going to be greater than all these. But we're not trying to offset all of our main loads, so that's fine. Well, that's really it. And look in again. We're going to go over an AC coupled self-consumption type of system and how we'd use this configuration tool to design that. Thanks.